Alrighty, today is the day. This is trust analysis. This is going to be probably the single-handedly most difficult subject matter of the entire unit. Please make sure you have a calculator, a pencil, and your notebook sitting next to you. Pause this video as many times as you would like. Rewind it as much as you would like. Try to understand this. We will go over it in class as well to make sure you fully understand it. This is a lot of trigonometry, and if you need to review your trig, go back and watch the trig ones because we're going to do both moments. We're going to talk about free body diagrams, force vectors, trigonometry. The whole bit that we've been doing in this whole statics unit is culminating to this video. So let's start off. All right, so forces. Forces can cause either tension or compression. Tension is when you pull on something and elongate it, stretch it. Okay, now we always point that the force vectors are always pointing away from the source that we're trying to bend. So it's always moving away from each other. This is tension. Compression is just the opposite. It's compressing. It's crushing something and shortening it. Then we always again point the arrows towards the middle. This is compression. Now let's define a truss. A truss consists of straight members that are connected to joints. Remember, a member is just a single piece of beam that makes up all of the a structure. Now, no member can be continuous through it, meaning this is not one continuous member. There's two. There's 1 and 2. They are then bolted together at joints. Most structures are made of several trusses that are joined together to form what we call the framework. Each truss carries the load which acts in that plane. So again, this plane which is going left and right and up and down that plane. And can be treated as a two-dimensional structure. Now, we bolt or weld connections are assembled together, but we can think of them as pinned. So we can actually, instead of just being bolted like this or welded, we can imagine them being pinned together. And the forces acting on the forces acting at the member ends can be reduced to a single arrow of force. Now, when forces they'll tend to either pull members apart. This is what we refer to as tension, or they'll try to compress it, and we call that compression. So it can either squeeze them or pull them apart, or in some cases, none of the above. So here is a simple truss. Member trusses are slender and aren't capable of supporting, and they're not capable of supporting large lateral loads by themselves. So one little beam here could not support a car. And even 2 or 3 or 4 of these, if you put 4 of those, could not support a car. But adding this truss here and on this other side, now you can actually cause that to happen. Here are some different variations of different trusses that we will see: Pratt's, Parker's, K-truss, Warren's, Camelback, Howell's, Bowstring, Baltimore, Pennsylvania, lattice, the Wattle. Here's some, you can see here, this one is a kind of it's a Parker. I believe that's a Parker. And you can see these thin, narrow pieces of beams, but that's going to support the whole truck. And a semi or several semis could pass on this without causing it to collapse. A rigid truss will not collapse under any force. Triangles are the simplest of those trusses. If I apply any amount of force on any one of these, it will not collapse under its own weight. But if you have something like a square, it will collapse. If I pushed on B, then B is going to collapse inward, and C will get kicked out, and you'll collapse it. But by adding more members, and so that triangles are formed, the structure becomes rigid. So if I connect B to D here, all of a sudden now it becomes rigid. Now we got to talk about reactionary forces. There are three common types of connections in which joins trusses together to the actual foundation, to the actual earth itself. There are rollers, there's pins, and then there are fixed. There is a fourth type not often found in buildings and structures, but it's called the simple support. This is often idealized with frictionless surfaces. We draw rollers with a circle with this line with a little bunch of hashes underneath it. That represents the ground. And this is a roller. A pin is represented by a triangle and attached to the hashes. A fixed, which is straight into the wall, and then the simple one, which we won't deal with. The fixed and simple we won't deal with in this, but you will see them later on if you go on into civil engineering, mechanical engineering. So if you have a rollers and pins is what we deal with. Rollers only have one force, and that is the force of the ground pushing up, reacting to the gravity of the entire structure pushing down. The pinned force, on the other hand, because it has also gravity pulling down, it's going to push back up, keeping gravity, abating gravity. But it also will have a lateral force. Because it's pinned, it can't move left and right. So if there's any force moving left, it's going to counteract it to the right, or vice versa. So rollers support are free to rotate and move along the surface upon which they roll and rest. The surface can be horizontal or vertical or sloped. It causes them to roll as they needed. So here's some different variations of them. This is the one we'll see. And here on a bridge is the actual roller. You can see how they have the three rollers, and this allows it to roll. This is going to allow it to roll and move as the heat, it causes the structure to expand. The Golden Gate Bridge, in its whole entire length of the Golden Gate Bridge, expands something like 2 feet. And if it didn't have actual rollers in it, they would actually buckle the entire thing, and it would actually fail. The whole structure would actually collapse. So they add this so that ever minute little heat or cold, it can actually stretch and move accordingly. Roller sports do not provide resistance to lateral forces such as shoving, winds, or earthquakes, and with those you're going to have different types of supports. Now, pin supports can resist both vertical and horizontal, but not rotational. They will allow it to move in a rotational, but not in a lateral motion. So you can see here is a pin, and it will resist going forwards or backwards or left to right or up and down, but it can cause it to bend if needed. These are the really common ones. You can actually go and see these type of pins throughout the cafeteria at the high school. So you can see different examples of pin supports. We will use this symbol for our pin, the simple triangle sitting on the ground without the ground representing as that horizontal line with the hashes. Now, fixed and simple we will not deal with, just know that they do exist. Fixed is like a flagpole being shoved into the ground. It won't allow it to move left, right, up, down, or twist. That's kind of a fixed. A simple support is just like a slab on just a flat surface. It's very similar to a roller, but difference between a roller and a simple surface is that the simple surface has friction. So it can't move very easily left and right, not as easily as a roller. And thus it stays put due to gravitation. And reality often depends upon gravity, friction, if it has any left and right motions. Very uncommon in today's world. Now, when we go into this, we're going to be looking at what is called statically determinate. What that means is this truss able to be solved in this future way. So in future slides when we talk about how to solve them, can it actually be solved? Because sometimes trusses can't be solved and are called statically indeterminate and can't be solved, and you just say, oh, it has to be done by a computer rather than by hand. Now, the equation is this: 2 times j equals m plus r. What that means is 2 times the joint numbers is equal to the number of members plus the reactionary forces. So let's look at this one. We can look at this and we can say how many joints. 1, 2, 3, 4, 5. That has 5 joints. So this is 2 times 5, 10, times the members, or is equal to 1, 2, 3, 4, 5, 6. So that's 6 plus the reactionary forces. This has 2 because this is a pend, so it's 1 and 2, and this has 1, so that's 3. So this is 2 times 4 equals 6 plus 3, so 2 times 4 is not, so this is statically indeterminate. We cannot calculate this one. Now this one, we can calculate it. How many joints? 1, 2, 3, 4, 5, and 6. So 2 times 6 is 12. And the members is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, it has 3 because there's 1 here in the pin, going horizontally in the pin, and then just 1 going vertically on the roller, so 3. So 9 plus 3, that is 12. This is statically determinate. We can look at this one again, and we can see this one. 2 times its joints, 1, 2, 3, 4, 5, 6. Its number of members, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, it's the same setup in the pins. One up, 1 horizontal, 1 up, so that's 3. And this one again comes out as 12. Now this one looks very similar to this one, but there's a pin in the middle. So we can look at it and we have 1, 2, 3, 4, 5 pins, so that's going to equal 10. And then we have the members, 1, 2, 3, 4, 5, 6. Again, remember that each member is these things, it's not a whole beam. And that's 6 plus 4, again, 10. So this one is statically determinate, this one is not. So you could not do this one. So now let's go over some equations, and then we will end the video here, and then we'll pick up another video here in just a moment. So the sum of the forces in the x direction must equal 0, meaning the sum of all my forces in the left or right direction have to equal 0. So that means if I have a force 1 plus force 2 plus force 55, it has to all equal 0. That means if I have an example problem, if I have 120 pound force pushing to the right, I have to have a negative 120 pound force moving to the left. Okay. Then we have our equilibrium in the y direction. It's exactly the same as by force direction. That means the sum of the forces in the y direction have to equal 0. That means all my forces have to equal 0. So if I have a force of 96 pounds down, I have to have a positive 96 pounds up. Moments mean that the sums of the turning forces, the turning moments, the torques, have to equal each other. So if I have 2 foot-pounds going in the clockwise direction, I have to have 2 pounds going in the counterclockwise direction. So I have a negative 2 foot-pounds. Okay, we're going to end the video here. Please rewatch that if it was confusing, and then we'll pick up the next video here in just a second.